And today we will see in detail the Klein Gordon relativistic equation. The relativistic Schrodinger equation is given by E squared is equal to P squared C squared plus M squared C power 4. And now you replace the energy and momentum by its operator. Energy operator is I. I h cross delta over delta t whole square, because we have to take the square. Let it act on the wave function psi. Then here the right hand side, p is in 3 dimension is equal to I h cross delta. So this will become minus I h cross delta whole square, and you have c square which will act on psi. And the last term is m squared c power 4. So m squared c power 4 psi. Now you just square it. You will get minus h cross square if you square the I h cross. Then this will be delta 2 over delta t2 psi, which is equal to, if you square the minus I h cross delta, then you will get minus h cross squared. Already there is c squared, and del squared psi. Then the last term you keep as it is. Now you divide both side by both side by h cross c square, h cross square c square. So you divide by h cross square c square. Here also h cross square c square, and here also h cross square c square. Then here h cross squared will get cancelled. You will get minus 1 over c squared delta 2 over delta t2 psi. Then the right hand side, here h cross squared c squared will get cancelled. So you will get simply minus del squared psi. Then what about the last term? This c squared will get cancelled with this c power 4, which will become c squared. So this can be written as m squared c squared over h cross squared psi. So now we will move on further. Now we got this expression 1 over c squared delta 2 over delta t2 psi is equal to minus del squared psi plus m squared c squared over h cross squared psi. All these are constant, remember that. You just compare the non-relativistic Schrodinger equation and the relativistic one. In non-relativistic, you will not get c square velocity. Velocity of light is not involved. We know that in the case of non-relativistic one, I h cross delta over delta t psi is equal to p square over 2m for a free particle. If it is not a free particle, then V will come. Now what is p squared? P squared is minus h cross squared. That is p squared is equal to, operator p squared is equal to minus h cross squared over minus h cross squared, I mean delta over delta 2 over delta x2. So you can compare this. Here it is first order time derivative and second order partial derivative. What about here? Here it's a second order derivative with respect to time as well as with respect to position. That is the main difference between non-relativistic equation and the relativistic equation. Here both are second order time derivative, both time and position. Then you rearrange this term. You bring first term to the left hand side, this to the left. Then you will get del squared psi minus 1 over c squared delta over delta t2 psi, which is equal to m squared c squared over h cross squared psi. So this operator is called D'Alembert operator. That is, it's represented as square 1 square, which is equal to del square minus 1 over c square, uh, delta 2 over delta t2. So basically the Klein Gordon equation is this square D'Alembert operator act on psi, which is equal to m squared c square over h cross squared psi. Now we will find the energy eigenvalue of Klein Gordon equation. Just now we have seen the Klein Gordon equation is del squared psi over 1 over c squared delta 2 over delta t2 psi, which is equal to m squared c squared over h cross squared psi. So now this plane wave is represented by psi is equal to, of course it is normalized plane wave. Psi is equal to e power I k r minus omega t. Now what is del square? Del square is equal to of course minus h cross square delta 2 over delta r2. uh, then this wave function psi. So if you differentiate with respect to r twice, you will get ik. First one ik you will get. Second time if you try differentiate, you will get another ik. So this will be ik square. In similar manner, if you differentiate with respect to uh, t, then first time you will get I omega, second time also, sorry, minus I omega, second time also minus another minus I omega. This will become minus I omega whole square. Now you take the square, ik squared is equal to minus k squared psi. What about minus I omega whole square? Is 1 over c squared already there. Minus I omega whole squared is minus omega squared. So already there is a minus here. Then there is omega squared. So minus omega squared, because minus I whole squared is equal to minus 1. So then it will, minus of minus will become plus. So this will be plus 1 over c squared omega squared psi is equal to the left hand right hand side m squared c squared over h cross squared psi. Now what I am going to do is I am going to bring this to the other side, that is right hand side. So this will become 1 over c squared omega squared psi is equal to k squared psi plus this m squared c squared over h cross squared psi. So we will reduce it further. Now we got this expression 1 over c squared omega squared psi, which is equal to k squared psi plus m squared c squared over h cross squared psi. Now you multiply this equation by h cross squared c squared. So the first term c squared and this c squared will get cancelled. You will get h cross squared omega squared psi, and here in the first term you are multiplying by h cross squared c squared, already there is a k squared here, and here if you multiply the second term of right hand side, the h cross squared and this h cross squared will get cancelled. You will get m squared c power 4. That means h cross squared omega squared is equal to h cross squared k squared c squared plus m squared c power 4. So if you take the square root to both side, that it will become h cross omega is equal to plus or minus square root of h cross squared k squared c squared plus m squared c power 4. Remember that here the h cross omega is energy which can take the positive value or negative value. So there is no explanation for negative value in Klein Gordon equation. So we will see it further. Now we will see the probability density. I have given one lecture on continuity equation for non-relativistic case as well as the relativistic case. For non-relativistic case, the probability is equal to probability density is equal to IH cross 2 m over 2 mc squared psi star partial time derivative of psi minus psi partial time derivative of psi star. So now you bring this IH cross inside here, IH cross. So similarly here, here it is bra vector, Dirac notation, it is psi. So you can take IH cross is an energy operator. Here is psi star, naturally this will become minus IH cross. So already there is one minus which will become plus. Here it will be IH cross delta over delta psi. So this is the energy operator. When energy operator act on the wave function psi, it gives the energy eigenvalue E. So this will become psi star E psi. Similarly, the second case, it is psi. When the energy operator act on psi star, it will give E psi star. So E is a number, eigenvalue, you can take it out. So E divided by mc squared psi star psi. The probability is E divided by mc squared psi star psi. Remember that E can take negative value. So probability can be negative. So we know very well that the probability cannot be a negative value. So that is the problem with the Klein Gordon equation. This negative value, negative probability comes because of this negative energy. Also, there is no proper explanation for the negative energy. So, from a Klein Gordon relativistic equation, these are the following these are the drawbacks. First one is no explanation for negative energy, and you are taking the energy as a square root. Just now we have seen. Remember that energy and momentums are operator. You have to take square root of the operator, which makes mathematics complicated one. And negative probability, which is not possible in realistic case. So probability is 0 to 1, and here spin of the particle is ignored. These are the disadvantage of Klein Gordon equation. In the next class, we are going to see about the Dirac relativistic equation. He cleverly overcome all these drawback, which we are going to see in our next lecture. Thank you very much for watching my video and supporting me continuously. Thank you very much.